Our next talk is by Captain Dr. M.S.N. Murthy. Captain Murthy is an alumnus of Naval College of Engineering INS Shivaji and Naval War College. He is an M.Tech in Thermal and Fluid Engineering and a doctorate holder from IIT Bombay with the research topic of combustion characteristics in gas turbine engines. He holds a patent on the innovative heat engine concept called part electric gas turbine through IIT Bombay and has applied for another 3 patents on simple and efficient fuel consumption measuring system for heat engines, recuperator for open architecture GT, and semi-closed PEGT for air independent propulsion. He is currently heading Center of Excellence Marine Engineering INS Shivaji as officer in charge. His talk is titled IoT and Digital Twin Based Situation Aware Smart Assets. May I now request Captain Murthy to take over the proceedings.
So the first speaker of this session has covered same topic on aviation assets. I'm going to talk about the naval part of it. This work is about how we can employ artificial intelligence and the tools that are developed current day in optimizing our naval assets. And this part of this work is being undertaken at the Center of Excellence, and Commander Apur Mayank is having a contribution in this work. Yeah. Okay. Okay. So, in the words of Mr. Jensen Huang, founder of NVIDIA, with perception AI, we can now understand images, words, and sounds. With generative AI, we can generate images, text, and sounds. And now we have agentic AI that can perceive, reason, plan, and act. So, current phase is agentic AI, and the final goal is the physical AI with robotics. So, agentic AI differs from traditional AI in its ability to understand and interpret complex, nuanced contexts and goals, allowing for more specific interactions and decision-making processes based on well-defined networks. While traditional AI operates primarily on specific algorithms using structured data and set rules, agentic AI systems are designed to be more autonomous and adaptive, processing data, making decisions, learning from interactions, and taking proactive steps towards achieving complex goals by anticipating needs and suggesting actions. But you see, the backbone of all AI is the database, the huge amount of database. So the source of this database is usually the internet. What happens to the defense forces and their data, which is not available on the internet? So there is a need to develop customized tools, probably using existing knowledge, but for the customized data to employ AI effectively in the defense forces. So a disclaimer before we go ahead, I have no specialization in AI or any related topics. What I am going to present further is about the potential application in the Navy. This content is security cleared from Navy, and it's been published earlier in 2 of the defense journals as shown. My topic is specific to the move component of the ship, which has the float, move and fight aspects for every warship, which means that it doesn't cover about the weapons, which was covered in the forenoon by the Admiral Superintendent Dockyard. So those similar parallels can be drawn in applications of this. First few slides are endeavored to familiarize the audience with the warships. Then I will share the challenges and opportunities in maintenance management of warships, where we look at the potential to use maintenance related data for from the sensors to create digital twins and induce situational awareness and decision support system based smart assets, followed by transition towards reliability centered maintenance. Then implementation and scaling up of the system before I conclude the key takeaways. So Navy is all about ships. Each warship is a complex amalgamation of multiple technologies and systems working together. So aircraft, we discussed earlier, has got the gas turbine and its own controls and the weapons and sensors. Ship is a larger platform and has got plethora of things. So you can see on the float section you have the hull, the superstructure, which is the raised part of it. It has the stability and damage control aspects, living spaces, stores, galleys, accommodations, all are part of this float component. The move component has got propulsion systems that includes the heat engines, whether gas turbine, steam or diesel engines, the shafting, reduction gear, propellers. Then the power generation gives the electrical power. There are multiple power generators for redundancy purposes. There is refrigeration and air conditioning, both for cool room space and human comfort and maintaining the temperatures of electronic compartments. Hydraulics, steering systems to steer the ship, stabilizers to keep the platform stable for firing weapons. You have plethora of auxiliary equipment like air compressors, which become the reserve energy on the ship. The reverse osmosis plants for continuous production of water, potable water, the oily water separating systems to keep the MARPOL compliance, the many number of centrifuges, pumps and various auxiliaries. We also have on the bottom section of the ship reserved for fuel tanks, lubricating oil tanks, water tanks, and a lot of space for spare parts, tools that are required to sustain the ship at sea. The fight component has the anti-surface weapons, guns and missiles, anti-submarine weapons, anti-aircraft weapons, armories to keep all these missiles and weapons, different sensors, radars for the air and the sonars underwater, and an integrated flight on most of the ships. So this is what the composition of the ship is. So as they're all meant for war fighting, reliable operation of these equipment at all times, each and every time when needed, is an absolute necessity. If any equipment of a ship doesn't perform or underperforms than what is meant for, it can be catastrophic for a mission. For example, a simple RO water plant that generates potable water on board, if it fails to work, it limits the endurance of the ship. So a fleet consists of multiple types of ships in various sizes with varying capabilities, whose design caters for different roles like aircraft carrier, destroyer, frigates, corvettes, tankers, hydrographic vessels, etc. A fleet is a very closely connected and coordinated team. Now, a ship which is part of a fleet, if it doesn't perform, it could be detrimental to the strategy employed by the fleet and can render the fleet handicapped for the mission. The same is applicable to multiple fleets that operate together as a navy for a common objective. It further extends to inter-services application in a coordinated manner. Thus, highly reliable equipment as well as redundancy become important elements of the ship design as well as her upkeep and maintenance. So it doesn't end here. So there are large support systems associated with the functioning of the ship back home in the ports and harbors where the ships are housed, which is essential for the ships to do their jobs. So they include the berthing facilities at the harbor, there are trials agencies which qualify, test the equipment, there are docking facilities for large-scale maintenance of the ships, there are larger maintenance routines that go on board, there is plethora of spares and tool support, and there is during the operations there is the support of the war room which controls and coordinates various things. So they're all laid out in multiple layers of the organizations. So the ships fall under the fleet, they're supported by fleet support units, and the fleet headquarters, there is a submarine headquarters, all of them fall under one command, and the command falls under the naval headquarters. It's all a tightly controlled and coordinated setup that has to function together. So how is this function of maintenance being done till now? So with the main objective to maintain high reliability of the ships and their equipment, the maintenance philosophy adapted plays a very critical role. Currently, planned preventive maintenance recommended by the OEMs is followed in the Indian Navy, as also was told in the Air Force. Tools like oil analysis, vibration monitoring, parameters trending have been adapted in the Indian Navy. However, there are gaps in effective utilization of these towards the final objective of highly reliable equipment. So these are integrated control systems. So compared to previous designs of warships, the newer vessels integrate the data from multiple sensors and provide to multiple sources to achieve high redundancy, integrated user interface with ease of operations. So you can see various sensors data being fed to a common distribution network from where the weapon systems are all able to use them effectively to deliver the ordnance accurately and reliably. So this caters to the fight component of the warship. So similar version of this is the so-called integrated platform management system or the integrated machinery control system, which caters for the float and the move components of the warship. As mentioned earlier, these are various engineering equipment and systems that are part of the warship. So this representative picture shows the power, propulsion, damage control, the auxiliary systems feeding their sensors data to data acquisition, which process the data and send to the data bus continuously. Various consoles across the ship can access this data to monitor, further process or control these systems from these consoles in accordance with the authorization and the security layers provided in the system. Currently, the control system of each of these systems are part of its respective system. Only the user interface is provided with the controls, in addition to the local control stations for the redundancy purposes. So this is also because we don't have access to the design of the control systems, being proprietary by the nature. Otherwise, the control systems can become part of the consoles. So the data flowing between the equipment and the HMI at various consoles is the targeted data to implement the IoT and digital twin based assets management that can provide situational awareness and decision support system. Currently, this data is only locally utilized for the ship's functionality and neither extended for any data analysis nor stored for posterity. Further, when it comes to ships of older vintage without these kind of integrated platform management systems, the traditional maintenance methodology is the only choice, which is limited to manual data collection. So this process is time consuming, human centric, prone to not only errors but also of conflict of interest. The sampling rate of this data is to the best monthly. The assessment of the collected data passes through a limits based approach of go or no go to qualify to be normal or abnormal for each parameter individually. So this methodology gives inaccurate assessments of the asset condition, resulting in either over or under maintenance, significantly affecting the maintenance strategy employed and the asset availability. Condition-based predictive tools are added to the traditional maintenance methodology, which rely on periodic inspections to assess the condition of the equipment. With a wider sampling rate, the actual condition of the equipment may not be captured at all times. It can predict failure and optimize the maintenance activities despite being cost and time consuming. Maintenance decisions sometimes are challenging to be taken for the risk of uncertainty involved. Thus, the OEMs are called upon to absorb this risk despite the very prominent existence of the conflict of interest. Thus, the traditional maintenance methodology is laden with unforeseen failures, unscheduled maintenance work, very precious operational downtime, sometimes jeopardizing mission critical activities. This impacts the fleet readiness and overall operational capabilities. This resulting uncertainty demands over maintenance and is usually compensated by excessive redundancy, including carrying excess spares on board, which is not a cost effective solution. Thus, in summary, the traditional maintenance methods are often reactive or time based, proving inadequate for modern naval needs. In light of the increasingly complex naval operations, there is a need for more sophisticated technological solutions. Global security landscape and advanced weaponry demand heightened readiness and emphasize the constant need to adapt to new technologies. The solution to these challenges lie with the reliability-centered maintenance achieved through continuous feed of the sensor data and twinning the system to predict failure and correctly assess the health of the equipment. Here, IoT will be the naval intranet, or probably it should be called as Internet of Battle Things or Military Things, as this data is not available on the internet. So this will facilitate proactive and predictive maintenance strategies, reducing downtime, optimizing maintenance and logistics requirements. This also aids in life cycle costing, which is important to make right choices in buying equipment. This helps institutionalization of the data and experience, especially relevant in our case where we keep moving every 1.5 to 2 years. So this maintenance approach indeed improves assets reliability and availability and also adds situational awareness and decision support through the data. IoT sensors capture equipment operational data such as temperatures, vibrations, pressure, and oil quality. So this real-time monitoring provides immediate insights into the health and performance of the naval assets, supporting timely interventions. The data is relayed to IPMS, that's the control systems, and served and saved as per the chosen sampling rate, which could be practically 15 minutes. Ships without this kind of management system can target the main machinery for like propulsion and power generation through their local control systems. This data is saved and sent out of the ship securely on a daily basis. So this data transmission to the reliability assessment center via satellite communication at sea or naval intranet in the harbor. This maintenance data entered manually in a templated format by the ship, trials agencies and repair agencies as per unique identity of the equipment adds on to the data that is being collected from the equipment. This data together now can be used for multiple purposes, including generating digital twins. So digital twins create virtual replicas of physical systems and processes, enabling simulations and predictive analysis based on real-time data. This capability allows for the identification of potential failures and optimization of maintenance schedules to avoid downtime. So we can move from preventive to proactive maintenance. So this strategy focuses on identifying potential failure modes and implementing measures to prevent them, enhancing assets reliability. Decision support system integrates data from IoT sensors and digital twins to provide actionable insights for the maintenance personnel. This helps prioritize maintenance tasks, optimize resource allocation, and improve overall decision making processes, not just for maintenance alone, but for the operations as well. Data from the Reliability Assessment Center is processed to a quantifiable numerical value based on multiple variables like spares availability, current performance, and various uncertainties as well. Though there are reliability engineering studies which can give quantitative assessments, here the qualitative assessments will actually do a good job. This numerical value, which may be called as reliability or a modified reliability number, is defined from subsystem to systems to equipment to functional aspects of the ship, and further can be extended to naval fleet. So this gives a near real-time assessment of the assets at various levels, facilitating decision support based on realistic situation rather than intuition or perception of or understanding. So IoT-enabled smart spares management system tracks inventory levels, predicts demands, and optimizes supply chains, which ensure that necessary parts are available when and where they are needed, reducing maintenance delays. It can also facilitate just-in-time concept, reducing inventory costs. Real-time data sharing among maintenance teams, logistics providers, and operational units ensures transparency and collaboration. This facilitates informed decision making and enhances mission readiness by minimizing downtime and optimizing resource utilization. Digital twins enable dynamic scheduling of maintenance activities based on real-time assets condition and operational requirements. This optimizes resource allocation and ensures that critical maintenance tasks are prioritized, improving overall fleet performance. Integrated platform management systems integrate data from various sources across the naval platform, including machinery, navigation, and combat systems. This integration provides a comprehensive view of the asset's operational status, facilitating better maintenance decisions. Knowledge graphs connect these data points across various systems to reveal hidden relationships and patterns. So this linked data provides enhanced insights, allowing for more informed and effective maintenance strategies and predictive capabilities. Some of the examples of these knowledge graphs are shown in for the 3 slides. This one is for the reliability centered maintenance, where the data is picked up from the ship level based on the real-time monitoring and the sensors. It's relayed to the shore-based processing, so where it processes failure detection and other analytics that are employed. A knowledge graph for enterprise level data management connecting the other units that are responsible for the overall functioning are shown here. Similarly, for failure prediction, the data is employed into various modules to predict failure to the accuracy that is desired. Like I said, a qualitative assessments do a great job in this case. So implementation, the short-term implementation involves focusing on critical assets. Pilot projects is currently in progress. So we are also making use of data simulators to match the gap of getting the real-time data from the ship. And the value of IoTs and digital twins will be employable qualitatively. So this is a quick win in the short term, and it also gives us the momentum for wider deployment. So the midterm strategy includes development of centralized data support system, decision support system, which integrates the data from multiple sources, provides actionable insights. This enhances the decision making at both the ship and the fleet levels. In the long term, would involve a full-scale implementation Navy-wide. This ensures continuous monitoring, proactive interventions, optimized resource allocation, and maximizing the fleet readiness. So scaling up, we are also progressing certain projects on wireless controls in a partial manner, where an equipment can communicate with their control systems partially wireless to provide a more cleaner environment in the ship. We are also working on coded controls that further enhance this attempt of data obtaining easily. and this also facilitates our indigenous IPMS kind of systems. So this is not limited to the just move component of the ship, but extended to float and the fight components as well. This approach further plugs into operational data of the ship, where there are several teams which are working on this. Navigational data like berthing charts across the globe in various ports, past records of navigational mishaps, weapons firing data, image recognition of aircraft, ships, last reported locations of ships, both the military and the merchant ships. They're all gathered together. They're integrated at fleet and war room levels, which brings the situational awareness component. And the captain or the commanding officer of the ship or the fleet commander who controls the whole fleet gets a complete picture, which facilitates him about what is the correct course of action through the decision support system. Otherwise, in absence of these information, he is only left to himself and his intuition. So when we talk about tri-services or the inter-services integration, the mode of interacting between the services has to be defined. So this kind of system becomes an essential requirement for this integrated setup. So it can further extend to other national resources, and this kind of system would provide the best utilization of national resources, as war is a collective effort. So to conclude, this census-based real-time asset health monitoring system is quite valuable. Optimized assets and spare inventory on board is possible through employing reliability-centered maintenance. So reliability is not associated only with the designers. Generally, there is a conflict of interest for them to share any reliability content. But as users throughout the life cycle of the ship, the content that user has in terms of data is very valuable, and that insights are valuable to the OEM also. But unfortunately, we keep depending on the OEM, who do a good job in designing, but they don't have much say into the as a user perspective of it. So here is our strength through which we can employ the reliability in exploiting the machinery. So the integrated functioning between the ships and shore agencies also helps in institutionalizing data and the experience that each one carries and hands over to the next generations. So there's a lot of risk and uncertainty to be absorbed in decision making process when it comes to split second decisions and courses that has to be decided, and they are accountable. So a support system like this is a very, very valuable instrument for the naval fleet. Life cycle management is another important aspect, where from the womb to tomb we can count how good is the machinery, and the procurement process of the equipment need not be based on the L1 alone, but overall reliability of the machinery will come into the play. So it brings in more accountability into the system. So this has potential to optimize the operations by dockyards and refitting agencies, as well as logistics management. So this provides enhanced fleet readiness and deployment efficiency. This as a product is employable for merchant marine as a maintenance enhancing tool for them, and also to friendly foreign nations who look for support in the Indian Ocean region. So integration with the operational data that I was speaking will provide the overall situational awareness and the decision support system for the warfighting effort, and this is the future for the inter-services integration. With that, I finish my talk.